Okay, so what I would like to do now, I would like to restore the H bar dependence. Okay, so I want to put H bar back into all of our formulas. And the reason for that is in that way, we'll be able to learn what is the classical result and what are quantum corrections. And you shouldn't be surprised to hear this, that there's a very nice way to simply read off what is the H bar dependence, how classical or how quantum is it, just by looking at properties of the diagram. Okay, so let's now try to restore H bar dependence. So I'm going to do that by asking a question, first of all. So what are the dimensions of H bar? Well, I think that you are all familiar with the uncertainty relation. Delta P, delta X must be greater than or equal to H bar over 2. And the reason why I picked this relation is that it clearly tells us that the dimension of H bar is the same as the dimension of delta P times delta X. And working out the dimensions of delta P and delta X is very easy. For delta P, it's a mass times a velocity. So it's a mass times a length over time, and delta X is a length. So in total, H bar is a mass times a length squared over time. Now, there's a very important quantity that has that same dimension, and that is the action. So let me try to convince you of that in the simplest possible setting. Let's just take the action of a free particle. So if there's a free particle, there's no potential energy, so the action is just given by the kinetic energy, okay? So if we want to work out what is the dimension of the action, well, we've got a length, that's for the dt. We've got a mass, m, and then the v squared gives us L over t squared. Okay, sorry, I misspoke. The dt gives us a time. Okay, good. Okay, so let's now multiply that out. We're dividing by time squared, but we've multiplied by time. So we'll get mass length squared over time. And that, of course, is the dimensions of H bar. Now, the nice thing about that is we immediately learn how to put H bar back into our formulas. Remember, the central quantity that we have been studying to calculate correlators has been Z of J. And Z of J takes this form. It's an integral d phi. Then we had e to the I, the action, plus integral d4x, j of x, phi of x. And now we've learned that the action has the dimensions of H bar. We know that we have to make the exponent dimensionless if this is to make sense. So if we want to put H bar in, that's where H bar goes. Okay, so let's just write this out in a little bit more detail so that we can see where is the H bar going. So we've got an E. The action will be an integral, d4x. Then we'll have 1 over 2 H bar d mu phi minus m squared phi squared. So those are the kinetic terms. And then we'll also have, let me not forget the I. And then we'll also have minus g, this is also over H bar, phi to the 4. And then we have that second exponential, integral d4x, j of x, phi of x, and we didn't touch that second exponential. So notice what's happened. So the first thing that is pretty obvious is from this g over h bar term, okay? So what does this mean? Everywhere where we had a g, we now need to replace it by g divided by h bar. So equivalently, each vertex comes with h bar to the minus 1. Okay. What's the second change that we've had? Well, it comes from looking over here. The quadratic terms in the action have been divided by h bar. But I want you to remember that g of x comma y, we found a very nice interpretation of it. G of x comma y is equal to the inverse of the quadratic terms. So we want to invert the quadratic terms. If we invert 1 over h bar, we get h bar. So g of x comma y becomes h bar times g of x comma y. So each line in the Feynman diagram comes with h bar. Great. Now let me make an important comment, and this is something that I want you to keep in mind. Let's maybe put it in red. It is kind of important. So comment. And what this comment is going to tell you, it's going to tell you what to look out for. So the overall powers of h bar reflects the dimension of the observable. So, for example, the action might be proportional to h bar, but that's just because the action and h bar have the same dimensions. So this is not too interesting, okay? And what I mean by that is there's no real dynamics there. It's being determined entirely by dimensional analysis. What is much more interesting is relative powers of h bar. So the relative powers of h bar tell us whether something is a quantum correction. So it's the relative powers of h bar that are the most interesting. If the leading term goes like h bar cubed, well, that's the classical term. And if the term you add to that is an h bar to the 4, well, that's h bar times the classical term. So that would be a quantum correction. So it's really, it doesn't matter what power in h bar you have. What matters is what power in h bar you have compared to the leading term. Now, let's just introduce a little bit of notation. So motivated by this observation of how the h bars come, I want to introduce the following. I'm going to say V is equal to the number of vertices. And then I could say, let's just count the number of lines, but I want to be a little bit more fine-grained. I want to count the number of external lines, and I want to count the number of internal lines. And it won't be obvious to you at this stage why I want to keep track of things in this way, but by the end of the next lecture, you'll see this is actually useful extra information. Then what is the power of h bar? The power of h bar is given by, it's h bar, each vertex comes with a -1, so we've got minus v, and each line comes with 1 h bar. So it's the number of external lines plus the number of internal lines. Good. So that's the power of h bar. So let's look at a few Feynman diagrams. So we could, for example, look at this Feynman diagram, or we could look at this Feynman diagram. So if we look at this diagram has got 2 vertices. This diagram, I'm sure you've got no problem with counting these now, has got 4 vertices. How many external lines? Well, those are the lines that connect to the dots. So there's 2 external lines in the first diagram and 2 external lines in the second diagram. So it's the number of dots. Then how many internal lines are there? Well, these are the lines that don't connect to dots. So they must pass between 2 vertices. So there's 3 internal lines in this graph. And for the second graph, there is a total of 1, 2, 3, 4, 5, 6, 7 internal lines. So let's just separate these two. For this diagram, we have got, let's write in the h bar, we've got h bar to the power of -2 plus 2 plus 3. So this would be h bar cubed. And for this diagram over here, we've got h bar to the -4 plus 2 plus 7. 2 plus 7 is 9, -4 is 5. So this diagram would come with an h bar to the power of 5. Great. We'll keep going in a minute.